x minus 3. Let me step back and look at it, make sure it does work. Looks like it does. Nothing cancels out here. Oh, is all the factoring correct, guys? Okay, so I don't think anything cancels, does it? So we need not worry about a hole on the graph. The one I did on Monday, there was a hole on the graph. There is no hole on the graph here, it doesn't cancel. Now, Michael, remind us, step 1, what does step 1 ask you to do?
Find the domain of R of X.
It says find the domain immediately. Well, I'm glad I factored here. I see quickly x cannot be -4, +3. That's all we want. X cannot be these two numbers. And that's all they want, and you get partial credit for that. Michael, what's step 2 ask?
Simplify.
Which we did earlier, which I'm glad we did. I'll just rewrite it. R of X, in that simple form, is 3x times x minus 1 over this.
Excuse me, sir?
Yes.
I left something over there. Can I take it?
Where's that?
I left something over there.
Oh, of course, of course. Over here? Yeah.
Where am I?
Okay, Michael, what's step 3? We got step 2 done.
The intercepts X and Y.
Okay, the x-intercepts, y-intercepts. Get ready for those.
Okay, very much. Have a good day.
Thank you, thank you. X-intercept. What's the fastest way to find the x-intercept? How do you find the x-intercept no matter what the function is? You said equals 0. Now, the nice thing about rational functions, guys, when I said equals 0, which I will, look at this. Here's my function in factored form. And you go ahead and just set that equal to 0. This. Now, I saw some of my students in my 4 o'clock session earlier doing something on an equation down in room 106. Guys, to solve that, what would you suggest I do to clean it up a little bit and make it easy on myself? Because I want to solve this thing for x. What would you do first in the attempt to do that? Anyway.
Cancel out the denominators.
You could multiply both sides by the common denominator, which is going to help because my denominator is x plus 4 times x subtract 3, and that means these will cancel on the left, which is nice. That merely leaves me, let me bring it up here, 3x times x minus 1, and of course when I multiply the other side by that denominator, x plus 4, x minus 3, 0 times anything on the other side is 0. So you merely end up with that. If you clear the denominator out. Now, one of my students in a previous class, and I agree with him. He says, Professor, I think to find an x-intercept on a rational function, it merely comes down to set this numerator equal to 0. You can do what I just did and clean it up, but it comes down to just that numerator set equal to 0. Now, if you split this up and try to solve, you got 3x is equal to 0. X minus 1 is equal to 0. Guys, you're going to get 0 here, of course. You're going to get a 1 here. And I'm going to write these as ordered pairs right here. 0, 0 is an x-intercept. 1, 0 is an x-intercept. Now, y-intercept, a little bit faster, a little bit easier, I think. To find a y-intercept, you find, in this case, r of 0. In other words, replace all the x's by 0. Guys, you know what's going to happen here. Replace an x by 0 on top and do the calculation, we'll get a 0. And on the bottom, it looks like you're going to get 4 times the -3, that's -12. Replacing x by 0. You're going to end up with 0. Which means that origin should be also the y-intercept. And it should be because the x-intercept is 0, 0. Okay? So we got the x-intercept, y-intercept listed. Is that true? Okay. Michael, what's number 3 asking?
That was number 3. Number 4 is
Or number 4?
the vertical asymptotes.
Good. Now guys, does anyone recall the fastest way to find these vertical lines that you cannot let the graph touch as I start graphing? Where are their locations? What's the fastest way to find the locations of those vertical aspects? Yes.
The denominator?
Set the denominator equal to 0. This is denominator. There you go. Soon enough, it is going to be, yeah, it said x plus 4, x subtract 3, that denominator equal to 0, and I'm here to answer already. Solve each one of these. You're going to end up with a negative 4 and a positive 3. Those will be the locations of those vertical lines when I finally get to the grid. Wow. Michael, how about number 5?
Determine the horizontal asymptote.
Now that can be tough. These markers, all these markers I have here, are working well. Number 5, a horizontal asymptote. Now, can anyone recall from Monday, what was that little lengthy process I suggested, the book suggests, I told you the many calc instructors suggest to find the horizontal asymptote. It's a little technique. Go for it.
Is that like divided all by x squared?
Divide everything by the highest degree you see. And guys, when I scan through what was given to me at the very beginning, the degree is 2. Just so happens, darn these markers, the degree is 2. And the degree is 2 also there. So if I say divide through by the highest is 2. So I'm gonna go here on the side and rewrite my original like this. I'm gonna divide everything by x squared. Minus 3x, divide by x squared. Denominator, everything by x squared, since x, the 2 is the highest, plus x over x squared, subtract 12 over x squared. And then simplify those from algebra. Guys, if we simplify that after we use that little technique, the first term, x squared's canceled, which is nice, just leave here 3. When I reach that second term, 3x over x squared from algebra, I can take x into x squared to simplify it and get an x. So that's 3 over x. Denominator, x squared's canceled out completely in the first term of 1. So this is a 1 here. Second term, I can cancel x into x squared and rename it from algebra as 1 over x. I can do this. On the end, 12 over x squared. If anyone can recall from Monday what I'm headed for, I can't simplify it, but I can rewrite it. What would be a way to rewrite 12 over x squared to lead me into what I need? Who recalls? I see, Abigail.
12 times 1 over x times 1 over x.
Perfect. She says, Professor, you can't simplify it, but you can rewrite it. Now notice those 1 over x's are coming up. So that means, in fact, it's 3 over x. I'm going to go back right now and change it. It is 3 over x. But for the purposes of what we want, let's rewrite it as 3 times 1 over x. Try and get that 1 over x in there as much as possible. Now, why is that 1 over x important here? What did we discover Monday?
It equals 0.
Exactly, look at this. Limit as x is approaching infinity of 1 over x is 0. If you make x get large, 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 1 over x, 1 over a large number, 1 over a large number, 1 over a large number, the values themselves are getting smaller, approaching 0. So everywhere you see a 1 over x in this little technique, you get to put a 0 based on this statement, which helps. And then you simplify it. Guys, on top I got 3 times 0 on the end, which is 0, it drops out, leaving me really a 3 out front. In my denominator, this is 0, of course. 12 times 0 on the end, drops out 0. I'm left with that 1 out front. After all that effort, it's 3. Whoa. So my horizontal line is going to be up at 3 when I finally get to it. I'm going to right here. Mr. Park, please tell me, remind me, in your calc, math 7 class maybe, or math 8, did they use this process like I'm doing, get the 1 over x in there to find the
Yeah.
Horizontal asymptote,
Yeah.
did they use the 1 over x?
Yes.
Did they also take advantage of this?
Yes.
Okay, so they did. Now, I'm not gonna give you all the details. That 1 over x has to be used based on this right here. We'll try to get that 1 over x. Now though, you can write yourself a little note. Don't tell them that Ramsey told you this. If they ask you to find the horizontal asymptote, and if, back at your original that Michael gave me, or Brianna gave me, if these degrees on the numerator and denominator are the same. Are they the same? Your horizontal asymptote, you saw what I had to go through to find it, is merely this number, this coefficient, over this coefficient. That tells you what the horizontal asymptote is going to be, which from calculus says, yeah, it is a 3. Now that is if they match up. Now there's some other cases where they do not match up, and that's going to be an issue. But right now, if they match up, it's easily seen as where the horizontal, or you can easily see where it is. Michael, before I leave it, did we also talk about a crossover point yesterday, Monday? Did we also ask, will my graph cross over the horizontal asymptote?
Yes.
I'd better get that out of the way right now. It may not here, I'll do it. Crossover. Is there a crossover point? And I'll put a question mark there, may not be one. My graph and the horizontal asymptote, will they intersect? Okay, guys, let's go back to my function. I'm taking the original, which is 3x squared minus 3x over x squared plus x minus 12. And I'm gonna set equal to the green here, equal 3, equal to my horizontal. Is my function ever equal to the horizontal? In other words, will they, on the graph, cross over, intersect? I'm gonna do a quick cross multiplication, guys. You guys who like a common denominator and so forth, you can do that. If you go, it'll do mine like that. So we end up with 3x squared subtract 3x in one direction. In the other direction, I got 3 times this. So we end up with 3x squared plus 3x subtract 36. This is things work out. Okay, now solve this. 3x squared will cancel. I got to solve this from algebra, guys. We'll move that 3x over, make this negative 6x. This is just algebra right now. Equals negative 36. Looks like x is equal to 6. At least there's an answer. Look at it carefully. Are we okay there? Is it 6? Is it quickly? If it is, that tells me when I get to the grid, out 6, and my horizontal asymptote was 3, so 6, 3 is a crossover point. Out 6 for the x, and then up 3 to land on the horizontal asymptote. Woo, this madness, madness, madness. Michael, maybe I'm ready to now go to the grid and put this on there, but let's see. Was there another part? What was the other part?
Determine the oblique asymptote.
Now that we have not discussed, and we'll do it today. So as far as this graph or function is involved, we have everything we need to get a sketch of what this looks like. And guys, the sketch itself. Try to find something here. Get a little better. On the side here, guys, let's try to put all the pieces together. Doing all that work on one side of the board just to go through those steps. Now the graph itself. We'll see. Okay, guys, on the grid, we go back and pick up step 1, of course, was the domain. Step 2, I think we found the x, or maybe step 3, the x and y intercept, and looks like I have 2 x intercepts, 0, 0, and 1, 0. Let me put those on there now. 0, 0, 1, 0. Those are the x-intercepts. Y-intercept, of course, 0, 0, I have on there already. Vertical asymptotes, we got two of those. Try to put those in red. Oh, I got red already. I'm in green then. I have -4 and a +3. These take so much time to graph. Guys, -4 right here is a vertical asymptote. Look like this. And a +3 out here. Those are my two vertical asymptotes. I have my x-intercepts. Got that done. Don't let me mess up now. No, I'm up the board here staring at it. Horizontal, we've determined it's up at 3. Up here. Guys, we use the different color for it. The horizontal asymptote is up here. Okay, guys, take a look at the grid. I hope you can see it from where you're seated. Horizontal, vertical, intercepts, and I have a crossover point, out 6, up 3. You're going to put that on the, you ready for it. Out 6, up 3 is out here. Stretch this out. About 4, 5, 6, up 3. So it's going to land right here as a crossover point. Let me step to the side. Is that true? Now, here goes. This thing is all messed up. That's why we finally have a quiz or an exam on this. You gotta be extra careful. Guys, how many pieces to this discontinuous graph, not connected graph, are there? It all depends on your vertical asymptotes. They're green. So there's something happening on the left. Got to graph it shortly. There's something happening in between the two green verticals, and there's something happening to the right. So there's 3 pieces here. Now you can plot a point. So if you want to know what's going on the left, Professor, you have nothing to work with out here. You can try -5 or -6 or -7, and be patient, and take them back and plug them in either here or here, and see what comes out and plot it, and see where the point falls. Can anyone tell me though, without plotting points, which you could, just see where the point is out there. Does anyone have an idea, Professor? I think I can see where the piece of the graph is out there without plotting points. Who has an idea? Out here to the left of -4. Where must that piece be? Who has an idea? And I could plot points, but just to save a little time, does anyone think they see where it is? And not plot any points.
Above the one?
Thank you. Isabella, is that you?
Yeah.
Say, Professor, I think it's over here. And follows those asymptotes. That's why those asymptotes are there. They're guides for this graph. Now, I've had students say, wait, Professor, why could it not have been like Isabella gave me? Why could it have not been doing this out there? This also follows the asymptotes. That follows the orange and the green. What's wrong with that one? It's going to cross the x-axis again. And I have no x-intercept out there. We found the x-intercept. There is none out there. So it could not be this one. That would save you a little time. Now, in between, I've got to pick up these 2 points. And, follow the best I can those vertical asymptotes. Does anyone have an idea, or I can plot points? How can I stay between here, pick those 2 points up, which I got 2, and graph it? Who has an idea? Follow the 2 vertical, pick up my intercepts, and graph it. Who has an idea? And you can always plot points. But just to save me a little time here, does anyone have an idea what it might look like in between? So you're saying maybe, Michael, to follow the vertical, get close to the vertical, but don't let it touch. It's gotta come up and pick up that. Right? And then it looks like it's gonna go across and come back and pick up the other x-intercept, which it's gotta do. And then come down, and he says, Professor, I think it's gonna come down and follow the other vertical asymptotes. Does that make sense, guys? Follows the two vertical, picks up the intercept. Now again, you can plot points. Many of my students will plot points to get a better sketch. Out on the right is where I gotta be careful. To the right of 3, there's another section of this crazy graph. And I gotta pick up that point. And I gotta keep in mind also I have a horizontal asymptote out there to worry about. Now that's the one that's gonna be a little strange. Who has an idea? And you could plot points. I'm going to put this in orange, I guess. You gotta get close to the vertical, the green. Get close to this, but don't touch it. Out here. And also come down and swoop around that orange. That's your horizontal asymptote, you're getting closer to it. But this one crosses over. Who has an idea of what it might look like? Describe it to me.
Is it like the same thing on the left side, but the arrows is like crossing over?
Much like this one right here, right? It is, much like what I do here. So he's telling me, Professor, it's gonna stay close to that vertical, don't touch it. It's gotta come down. I'm gonna do this. And it's got to, in this case, which is very, very strange, it's gotta come down and pick that point up and cross over. Now when it crosses over, it still stays close to, that's why that horizontal asymptote's there. Still stays close to, something like that. The asymptote does not cross over and do this. Got to stay close to that horizontal asymptote. And there finally is your complete graph. These darn things take me as an instructor a good maybe 25 minutes. That's what make you as a student, when you finally see one of these, a good 25, 30 minutes to get everything together. And then I've got tons of questions to ask about this. Isabel.
What determines if the parabola is upside, like facing down or facing up?
Beautiful. Here we go. Here we go. You mean the part in between?
Yeah.
Beautiful, beautiful. Tell me. After a little practice here, you'll see. Good question. She says, Professor, why didn't you make that parabola look like this? Cross over, pick that point up, and follow those two green vertical asymptotes, something like that. I think that's what she's asking, right?
Oh, is it because it's crossing twice?
Thank you.
Oh.
If you do it in that direction, without plotting points, are you going to cross over that horizontal asymptote again? And how many crossover points did we find? Only one. So I can't cross over it again. Oh, beautiful question. Absolutely. So it cannot be like that. Guys, anything else on this shape? Okay. So we'll accept this as my graph. That's a picture of that crazy function right there. Yeah, go for it.
After it intersects the horizontal asymptote, does it start increasing again and just ride that?
I got you. What it's going to do is, it's going to gradually start dropping down a little, just a little. And it's going to stay so close to that orange line there. And in other words, it's not going to do this. Is that your concern?
Yeah, that was kind of.
It's going to hug around, it's going to stay close to, hug the orange horizontal asymptote. Okay, so make it drop down. Okay? Mr. Park. Okay, I've got a question for you real quickly. He's brought a good issue here. Mr. Park, if my students were asked now, and you've got to keep my guys, the function's back here. This is how much work is required. The function's back here. That's its graph. We're still talking about the same function. Now, if I go back to this function and ask Mr. Park's help, Mr. Park, either in this form, 3x squared minus 3x over x squared plus x minus 12, or the factor form may be better for you, it's up to you. Would you please find this for me? What's r at 25? I would not want to put 25 for the x's in myself, but just out of curiosity, what's r at 25 on that function? Algebraically.
What's the function?
How much?
It's x plus 4 at the bottom, right?
That's an x, yeah, plus 4, x minus 3. Replacing x is by 25.
I got 2.8.
2.8.
Yeah.
Here's your question. This was 6 here, out of 6. I said, Scott's 25. I'm not here, so I asked him to find, where is my graph at 25? So he plugged in 25 into my function, he says, Professor, it's 2 point, how much?
8.
2.8, which means it's below, and by the way, was that green, was that orange horizontal asymptote up at 3? And we said it's down below. So way out here, it
Yeah,
still hovers around it. In fact, way out here at 25, it's what, 2.8? It's still close to 3, right? So if I can put 1,000 in there, find R and 1,000, guys, you're going to still have an answer coming out. Guarantee if you did it algebraically, you'll find the answer will be close to 3 again. It gets closer and closer and closer to 3, but it's underneath 3. Hovers around. Good question though. Good. Guys, any concerns here? Now let's close this down. Now you feel good about the graph. Few questions here. I'd like to find the limit, right here. You guys with me at 4 o'clock, one of my former students stopped by and talked to the class, and she's telling us in Math 7, the very first week or whatever, first few days, they're discussing limits. Okay, I'm gonna find the limit of this function as x is approaching, here goes guys, infinity. Make x get large, and tell me what my graph's doing. And if I say x is getting large, I'm saying I'll stop at 6. But no, you continue on the x-axis. And as you walk this way forever along the x-axis, you're pulling that graph along with you. What's the graph getting close to as you have it and pulling it along with you as you walk this way? What's it doing? What's its behavior? What's it getting close to? 3. Does it ever get there? No, it's approaching 3. Now, let's check the other end. This is like M behavior. Limit as x is approaching negative infinity of this function. So now it says, let's walk this way. I stopped at -4. Keep walking this way along the x-axis to the left, but drag that graph along with you, the blue graph. If you drag the blue graph along with you, what's it doing? Is it getting closer and closer and closer to the orange 3? Is it, guys? Does it drag along? So 3 again. In behavior. So those are 2 limits I could ask you. On the side here, I could also ask you to find this. I think we discussed this on Monday. On the limit, as x is approaching, here goes, guys, I'm going to try 3 from the right of this function. Superscript of a positive sign. There's the 3. Please come in from the right, stay on the right, and come in toward 3, something like this. Moving in that direction toward 3. What's my graph up there doing the closer you get to 3? Is it going up this way? Described as positive infinity. If you find the limit as x is approaching, I'm going to try another approach here. Let's try -4 from the left. Superscript of a negative sign. There we go, guys, -4 from the left. Here's -4. Stay on the left-hand side of it. So you're coming in this direction, you're getting close to a -4. I would know what my function is doing. Now guys, what's my function doing here? As I come in this direction, what's my blue graph doing?
Rising.
Is it rising also through infinity again? Okay? So I could ask you a few questions. Geez. All this space for the one problem. Likewise, I think that was just one problem, wasn't it? Okay. Now, I'm looking at my time because I want to start chapter 4 tonight. Also, I have not mentioned oblique asymptotes. I know right now as a student, if you're brand new to this, you've never seen this ever, you're brand new to this, you probably feel overwhelmed right now. Professor, my goodness, I've never seen a vertical asymptote in my life. I didn't know what they meant. I've never seen a horizontal asymptote, professor, in my life. And a crossover point and a hole on a graph exists. Now they end chapter 3 with one more type of asymptote, as if you don't have enough to worry about. It's called oblique. An oblique asymptote. Oblique means not straight. So this vertical, these are two vertical straight lines. Horizontal is a straight horizontal line. Wait till you see what happens, and we'll do one today with you. When the asymptote is not horizontal, it's not vertical, it's this. It's slanted. That's not your graph, that's an asymptote. And you've got to make the graph approach it. Now that's going to be interesting to see a slant or an oblique asymptote, and that's what chapter 3 closes down. Guys, where I erase all this is that now some of this is coming together. I hope you don't forget this during spring break, because I think I've given you enough little exercises to practice with, so I'm gonna keep you busy during spring break. Because I got a lot of things we'll collect from you on Monday when you return. I'll let you know more about that in the class. Okay, guys, no questions here? Michael, tell me what the next one of the 4 down there, I'm gonna do the 4th one, I don't think. What's the next one? Tell me what it looks like.
2x squared minus 5x plus 2 over x squared minus 4.
Okay, that one has another horizontal asymptote, like this one does. Okay, what's the last one?
X squared minus x minus 12 over x plus 1.
Ooh. That one's a different story. Now, when I jump into this and do it, here we go, make room for it here. Now guys, I think every day I come in here, I tell you guys, I've been bragging on you. We instructors talk. So when we get into our little private offices, we chat, we talk. I don't want to see that class drop down to 4 students or 2 students. No. Okay, here goes, guys. Michael, let's close this down. I'll have to do a recap with all this and then return. You said R of x is equal to, remind me what it was again?
X squared minus x minus 12
Over
x plus 1.
x plus 1. Guys, here goes. Now, can anyone tell me, the last one I'll be doing today, what do you notice as a student about this that I plan to do now compared to the one I just finished up? Now, you might see when a so-called oblique shows up. You might be able to tell early on, this thing's going to have an oblique, not a horizontal. Does anyone see a difference in the one I just finished up, just the function itself over there, and the way this function he gave me looks? What's the big difference? Go for it.
The degree on all is higher.
Thank you. The degrees are not the same this time. Over here, I think the degree on top is what, 2? The degree down here, what's also 2? The highest exponent on the numerator, highest exponent on the denominator, 2. They're matched up. It could be 3, 3, 4, 4, 5, 5, as long as they match up. You get a horizontal. Here, he's telling me, wait, professor, they don't match up here. This degree is 2. This degree is not 2, it's 1. Right? Now, you say, Professor, could you have maybe a 4 on top and a 2 on bottom? And therefore they're not equal. Maybe a 4 on top, a 2 on bottom, you could. You could have a 6 with a 3 on bottom, 6 on top, 3 on the bottom, but they're not the same. Now, if they are not the same, and we are lucky here, if they are not the same, your textbook only treats this type. If the one on top is exactly 1 larger, is the degree on top exactly 1 larger than the degree on the bottom? In other words, it's 2, 1 larger than the one on the bottom there. That says you're going to have a linear oblique. Like that straight line, that slanted line I illustrated, you're going to have a linear oblique. Now, can someone tell me, it's not going to happen here. Suppose this were a 4 and this were a 2. The top one's a 4 and the bottom one's a 2. What type of an oblique asymptote do you think that might result in? Anyone? Just out of curiosity. They differ by 2. There you go. There were a 4 and a 2, they differ by 2. So more than likely you'd have something like a parabola on your grid. Look at this, guys. This is crazy. It happens to them. You say, Professor, that's the graph. No, that's an asymptote. Your graph is out here somewhere doing this business on it. It's following it, maybe out here somewhere doing this. And then maybe, who knows what's going to do on the other side there. It's going to follow that green parabola. But your graph itself is going to be in orange. That could be an asymptote. I'm going to stay away from those. I'm going to stick with, as your textbook suggests, only linear asymptotes. So this one, guys, will have a linear oblique asymptote. Okay, here we go. Now, Michael, here we go. Finish this up. An oblique asymptote. I will still go through all my steps, so we'll do it fairly quickly. Step 1, I think it was to list the domain. Well, I see what you gave me in the green up here can be simplified. I'll do a little factoring. Factors into this. I think I did the factoring correctly. Nothing cancels, thank goodness there's no hole on the graph. And then step 1 always asks for the domain. In this case, x cannot be a -1. That's easy seen. You can't end up with 0 denominator. Michael, I think step 2 says now write this in simple form, which we've already done. So I'm just leave it as x subtract 4. Guys, I hope you can see this orange color here. Not that you know. There's the simple form. 3, if I recall, you've got to find the x and y intercept. Same process. Watch carefully, I'm closing all this down. X-intercept, you set the function equal to 0. So that means you will take the factored form and set equal to 0, or the green and set equal to 0. It's up to you. I'm going to take the factored form. That's my original function. And set that equal to 0. And we know what's going to happen. Cross multiply, you're going to eventually just end up with, as a student in a past class told me, you will merely end up with the, let's put it down here, the numerator set equal to 0. So to find the x-intercept on a rational function, it comes out of that. Just set the numerator equal to 0. Solve this, you're going to end up with a 4 and a -3. And guys, I realize these are tedious and they're time consuming. But this is the last one I'll be doing today. Y-intercept, do not let me make a mistake. That is really going back, replace all the x's by 0. If I do in the green, I see a -12 over a +1, so -12. If I have no mistake, 0, -12. It's my y-intercept. You guys agree? So far, so good? Whew. Number 4, I think, Michael, remind me, I think the rest are for the vertical asymptotes.
Yes.
Okay, guys, you know how to find those. You set the denominator equal to 0. That means I set my x plus 1 from my function equal to 0. Yes, right here it is. I have 1 vertical asymptote on this one, not 2. Look at it, -1. Number 5. Now, Michael tells me from the handout, it says, now find the horizontal asymptote. Guys, if we've already detected that this has an oblique, it cannot have a horizontal also. So I get to skip this one. This one does not have a horizontal. Okay, so there is none. No horizontal asymptote. It cannot have both. Don't have to worry about this, thank goodness. Now, number 6, yes, there is an oblique. Linear oblique asymptote. Wow. Now the process to close this down and start graphing. Watch carefully. The process to see where is this thing located. Where is this slanted line when I get to the grid, Professor? Where is it located? I knew my horizontal was located up at 3 on my last problem. No, this has an oblique asymptote. Guys, the process is to find where it is, go back to your function. Here it goes. And perform long division. Divide it out. Divide x plus 1 into, watch carefully, into x squared, maybe minus x squared minus x minus 12. We just divide this out. Now, sometimes I ask students, do you recall somewhere something called long division somewhere in your math background? Some say they do, and some say they don't. Here goes, guys, we'll try to describe the best I can. To do long division, you start out with asking yourself, how many times will the first term of the divisor, they call that part out front the divisor, go into the first term of the dividend? So in other words, x squared over x. That's where you're going to get your start. So guys, what is x squared divided by x, which on the side looks like this? That simplifies merely into what? X. That's your start. There. Now, if we're going further, please tell me, if I were across the street, teaching in the middle school, and you saw this, let's say 15, and just make up one real quickly. Those kids across the street are doing 15 into 402. And they call it long division. You first say what? 15 into 40 at the most goes how many times? 2. That's the same thing I did here. And then what are you going to do next? Then you went to from the middle school. What would you do next after you took 15 into 40? It goes twice at the most. What'd you do then? In your little process, who would you call it? Long. Did you multiply these two together? 2 times 15 got what, 30? You place it here. That's what I'm gonna do here. That's like at x, I'm gonna take x times x plus 1. So I take multiply, I will find the product of x times x plus 1, guys, which is x squared plus x. What did you do after you got to 30? From middle school, what was your next step? Who recalls? Subtract. So before I subtract 30 gives me a 10, then you bring down your next term and you start all over. Now you ask yourself, how many times will 15 at most go into 102? Now I think in my case it's what, 6? At most? I think it's 6. Is it 6 or 7? 6. 6. What are you going to do with that 6? 6 times 15, like you did last time, that's 90 in our case here. Subtract again, and you end up with, looks like maybe a 12 hanging on down there. What was that 12 known as? Back then? Remainder. So you got a divisor, a dividend, this is vocabulary, remainder, quotient. I'm gonna do the same thing here. Okay, x times x plus 1, I did my product. Now I gotta subtract. You guys told me to subtract 30 over here on this one, and we're gonna subtract here. To subtract here in the algebra says just change these signs. That's subtraction. Put them together, the x squareds drop out, and we end up with a negative 2x. Then bring down my last term, like I did here with my 2, and start all over. Guys, how many times will x go into a negative 2x? In other words, a negative 2x over x. What are you gonna get for an answer there? Where the x's cancel? And give you a negative 2. Put a negative 2 up here. And that's much like back in the middle school, we got that 6. And then you can multiply these two together, negative 2 times x plus 1, multiply these two together, you get negative 2x, what's your sign here? Minus 2. Negative 2 times that divides it. Subtract, like I subtracted 90 on that middle school problem. Subtraction for us, of course, means change these signs. 2 x's will drop out, I'm gonna end up with a negative 10. I think. That's my remainder. Woo! Long division. A long time since I've seen long division. But you gotta do a long division for this. Now you say, Professor, what on earth does that do? Please tell me, is this part that's left over, that's x that's left, right? I got x minus 2 up here. That part, just right there, that part, is that in the form of this? Does it look like that? That's what I'm looking for my straight line. Except it's gonna be an oblique line. It's gonna be a line with a slope of 1 and a y-intercept of negative 2. That's gonna be my oblique when I finally get to the grid. Guys, I'm gonna name it right here. The oblique will be named as y is equal to, by that long division process, x subtract 2. Whoa. Okay. Crossover point, usually, but I've seen some do this. The graph may cross over its oblique. I'm not gonna check this one, I don't think it does, to save you a little time here. I always check it for the horizontal, if there's a crossover point, like there was a crossover point on the last one. The oblique, it can happen, very seldom, so I'm not gonna test this one. And I think with all that said, there's no hole on the graph, we got enough to graph this. Go for it.
What happens with the remainder?
Beautiful, that's exactly what I thought was shooting at. You said, Professor, what happens with this remainder? As soon as I get that mx plus b that I need for the form of a straight line, drop this. The remainder will play no part on this. I'm looking for that mx plus b form. Good question, just drop that remainder. Has no effect on what we want here. Hope you guys can see what all this put together looks like, and then we will close this down. I'll see you guys a week from now, or the Monday for the return. Okay, the graph itself. Here it goes. And don't get angry, don't get frustrated, just say, I've gotta do it. Some parts of this course is more demanding than others. This rational functions section is demanding. Parts on here, if I can. Okay, going back to what all these steps tell me, I'm trying to find an intercept. Yeah, I got a 4 and a negative 3. Put a 4 here. X-intercept. It also looks like in that orange negative 3. Here. Just gotta practice with this. Y-intercept, oh, there is one down here, negative 12. Guys, if you don't mind, mark it right here. Show negative 12. Oh, this is gonna be an interesting graph. Vertical asymptote, oh, there's one down at negative 1. Like I show right now, that's the vertical asymptote. Down here at negative 1. Aaron, you were telling me you're interested in engineering, right? Get ready. Get ready for all this math. What else do you have here, guys? I got that. Oh, no hole on the graph. Now I'm ready to show that oblique asymptote. I'm putting in green. Now, I need to graph this right quickly. They can use mx plus b. That's just like a slope intercept form for a line. Or you look at it and say, Professor, I think I can find the x and y intercepts real quickly for this. But where is the x intercept just out of curiosity? X minus 2. You set equal to 0 and solve for x, you get what? 2. Y intercept, replace x by 0. You get negative 2. It might be best just plot the x and y intercepts for the green and say, Professor, there's an x intercept at 2 for the green. And there's a y intercept for the green, when I replace x by 0, it's down here at negative 2. It's here. And connected, my oblique, some textbook will call it a slant asymptote, is not a straight horizontal line like we're accustomed to. It's this. It's called an oblique asymptote. Of course, it runs forever. Are we okay? Lord, we don't have, that's not the graph. It's just the intercepts and the oblique asymptote and so forth. Now, you say, Professor, where's the graph? Well, there's something happening to the left of this red vertical, and there's something happening to the right of the red vertical. There's only two pieces here. And I gotta follow the green. The green is an asymptote, I gotta follow it. Guys, to the left, does anyone have a clue? How can I pick up that point there on the left and follow and get close to the red, don't touch the red for sure, and also follow the green? What would that look like over there? To pick up -3 and follow the red and follow the green. Over on the left. What's it gonna look like if I make a connection? Any ideas for I do it?
A V,
To begin.
a V shape,
What type of shape?
a V shape?
A V-shaped, Isabella. Let me ask you this. If I do this much, is that much right there following the red vertical? Can't touch it though. Must it also now swoop down, in this case, and also show that it's also going to follow the green? Oops, I'll make a curve too much here. The green oblique. It's going to follow both. Just going to swoop down like that, and no little curve to it. Looks like a little curve here the way I mark it with the marker. Smooth the little graph there. Follow those green and red. On the other side, it's got to do the same thing. It's got to follow the red and green. On the other side. And I don't think I'm going to have much choice. Let's see if I do, guys. I got to pick up 4. So it's got to do this. Pick up my y-intercept. Make sure I smooth this thing up through here. Come on up, pick up 4, and follow the red and the green. And make it look something like that. Is that reasonable? Had to follow the green, had to follow the red, pick up my intercept, there's the red. Jeez. Mr. Park, get ready, because we're closing this down. Here's the question. The way the graph looks, if we accept the graph, and by the way, the graph is in blue. Got the green, the red, those are asymptotes. If you're asked, I'm first asking my students, and then Mr. Parker's going to confirm it. Here's my function that graph represents. Can anyone tell me what on earth would be a value of this right here? Let's try to find R of 2026. Now me, if I were a student, you'd say, Professor, please, you know what, please, you're not gonna have me go back and put in 2026 for all these x's. Look at the very first term, we got squared. For all those x's, replace by 2026. Crunch it out and get an answer. Can anyone tell me before Park does for me? Because he's gonna actually put in 2026. What do you think I could do easily. It may not be exactly what I want, but it's very close to what I want for an answer. For R at 2026. Yes.
Just plug it into your, oblique asymptote.
Now tell me why. Genius, genius. He says, Professor, go back to this is your oblique asymptote, wasn't it? He says, replace X by 2026 there, not back there. 2026 minus 2 gives me what, 2024. So I would say this is close to, where was that? I was back here. Close to 2024. Can you tell the class why would you suggest to put it in here and not here, because Parks will put it in here for me. Why would you do that?
Because that line is just gonna keep falling your.
He says, Professor, the way the graph looks, your blue graph, which is the blue is the function, is the function getting awfully close to the green as it goes out this way? So why not way out there? It should be very close to the green. Way out there is going to use the equation for the green oblique asymptote and not the original function. So they should be very, very close to the same value. Mark, did you put in 2026 into the original?
Yeah,
What did you get?
I got 2025.
Wait, you got how much?
2025.
What did we get? Oh, we got 2024, I guess, right? So we were supposed to be close to 2024, and you said we were close to what, 2025?
Yeah.
Okay, let me ask you this. Oh boy, here goes. I have put in a number of what? I should find R at 2026. Lord. Try R at 10,000. Can you plug in 10,000 real quickly with your AI generated chat GPT? Putting 10,000 into that mess.
Yeah, I can't see it. My eyes are bad.
Tell us that's what you get if you put 10,000 in for all the X's back there in that green, which I would never ask a student to do.
Yeah, I got 9,998.
9,998.
Yeah.
Hang on now. When you did over here,
Yeah.
9,998, like that?
Mm-hmm.
Now, if I go to, as suggested, and put in here, 10,000.
Mm-hmm.
10,000 minus 2 there would give me what?
9,000.
9,998?
Mhm.
So why not put it in here? Much easier, 10,000 minus 2 than the original. And my student told me exactly what I wanted to hear. He told me, he said, Professor, way out there, they're so close together, the oblique and the graph itself. Why not just use the oblique to get that approximation? Wow. Guys, I know I wiped you out here. I know it's time for a break. It took me all this time to close down chapter 3. I know I see some looks on faces like, whoa, Professor, I'm going to enjoy my spring break, but when we get back, I know that we're going to really understand on these rational functions. Oh boy, this is going to be a mess. This is one of the hardest parts of the course, I think. These are rational functions, straight, horizontal, vertical, oblique, crossed over, this and that. And I have students every semester. I don't know you get all my students that well in this class. I know most of you guys pretty well now. But many of my students in the previous classes always ask me, right here, Professor, can the blue graph, since it's going way out there in space, and it's getting closer and closer to that green, could it eventually cross over the green? Could it finally cross over the green like I crossed over that horizontal back here on this one? And sometimes it can. Okay, I'm not gonna test to see whether this one will or not, but sometimes it can. Are we okay, guys? Okay, we need a break. Let's get a little quiz tonight, don't we? Yeah, you guys take your 10-minute break. Whew. Enjoy your 10 minutes.